This video will explore concepts related to forces due to magnetic fields. We will analyze how magnetic fields can exert magnetic forces on both moving charges and current-carrying conductors. We will state the equations for the magnitudes of these forces, and we will show how to use the right-hand slap rule to determine the direction of the forces. We will end this video with a study on the magnetic force between parallel current-carrying wires. Let's begin by considering the motion of a charged particle in an external magnetic field. If the charged particle has a velocity that is parallel to the direction of the field, then the charged particle will not experience any magnetic force from the magnetic field. However, if the charged particle moves in any other direction that is not parallel to the magnetic field, it will experience a force that depends on several quantities. In particular, the magnitude of the magnetic force on a moving charge is given by the following expression, where Q is the charge of the particle, V is the velocity, and B is the strength of the magnetic field. This angle θ is measured between the direction of the charge's velocity and the direction of the magnetic field, and dictates how strong the magnetic force is on the charged particle. The SI unit for the magnitude of the magnetic field strength, also called magnetic flux density, B, is the Tesla. We can rearrange this expression for B to see how the Tesla relates to the other units. Since sin θ is unitless, we find our magnetic field strength of 1 Tesla produces a force of 1 Newton on a charge of 1 Coulomb moving at 1 meter per second. From the expression for the magnetic force, we can deduce that a charge that is stationary in a magnetic field will not experience a magnetic force. Notice how this is different from the electric force on a charge, which is always non-zero even if the charge is stationary. The magnetic force also depends on the angle between the charge's velocity and the magnetic field. A velocity parallel to the magnetic field will have an angle θ equal to either 0 degrees or 180 degrees, and the sine of these two angles is 0, which reaffirms that charges with such velocities experience no magnetic force. Meanwhile, since the sine of 90 degrees is 1, a charge moving perpendicularly to the magnetic field will experience the greatest magnetic force. We can determine the direction of the magnetic force on a positive charge moving in a magnetic field using the right-hand slap rule. The right-hand slap rule works as follows. Hold our right hand out as if we were going to shake hands. The thumb should point in the same direction as the velocity of the moving positively charged particle, and the 4 fingers should point in the direction of the external magnetic field. The direction of the magnetic force on a positive charge is then given by the direction away from the palm of the right hand, the same direction as when we move the right hand to slap an object. So we find that the force due to a magnetic field is always perpendicular to the velocity of the charged particle and the magnetic field. In this example, we have a positive charge moving upwards in a magnetic field that points to the left. By aligning our right thumb upwards and the 4 fingers to the left, we see that the palm points out of the screen, so the magnetic force on this positive charge also points out of the screen. Notice how we have stressed that this right-hand rule gives the direction of force on a positive charge. If the moving charge is negatively charged, such as an electron, then the direction of force is opposite to that given by the right-hand slap rule. So if instead we had a negative charge moving upwards in a magnetic field that points to the left, we will still align the right thumb upwards and the 4 right fingers to the left. However, the force on the negative charge will be given by the direction toward the palm of the right hand. So in this case, the force would point into the screen. Since the magnetic force is perpendicular to the charge's velocity, the charge will follow a curved path. In particular, if a charge Q with velocity V moves at right angles to a uniform magnetic field, then this path will form a complete circle and will result in uniform circular motion. There must be a centripetal force to follow a circular path. and the magnetic force always points towards the center of the circular path, so the centripetal force must be provided by the magnetic force. Moreover, we can obtain an expression for the radius of this circular path using the following expressions for the magnetic force on a moving charge and the centripetal force from the data booklet. The magnetic force simplifies to QVB, as the charge moves at right angles to the magnetic field. This can be equated to the centripetal force, and then rearranged to make the radius the subject as follows. From this, we can see that heavy or very fast charges will move in larger circles, while large quantities of charge and stronger magnetic fields will result in smaller circular paths. And this result forms the basis of how particle accelerators are built. Let's now consider a straight wire placed in a uniform magnetic field. Recall that a current is a flow of electric charge. Since a moving charge experiences a magnetic force while placed in a magnetic field, a current-carrying wire placed in a magnetic field must also experience a magnetic force due to the forces acting on the moving charges in the wire. This also means that when there is no current in the wire, there is no force acting on the wire as there are no moving charges. When a current directed towards the screen is passed through the wire, a circular magnetic field is produced, which has a clockwise direction from the right-hand grip rule. This circular field will overlap with the external field to produce a resultant magnetic field which resembles something like this. The resultant field is strengthened above the wire, since the magnetic field of the wire points in the same direction as the external field. But below the wire, there is some cancellation of the fields due to them pointing in different directions. The imbalance in magnetic field lines will result in a force on the wire in the direction away from the stronger field. So in this case, the wire will move vertically downward. We can think of these field lines as the stretched elastic of a slingshot before the object in the slingshot is fired. This magnetic force on a current-carrying wire in a magnetic field is known as the motor effect, and is used in rotating wires in electric motors and producing sound from loudspeakers. Similar to the case of a moving charge, the magnetic force on a straight current-carrying conductor has an associated magnitude and direction. The magnitude is given by the following expression, where B is the strength of the magnetic field, I is the current in the conductor, and L is the length of the conductor that is in the magnetic field. The angle theta is the angle between the direction of the current in the conductor and the direction of the external magnetic field. Therefore, the force on a straight current-carrying conductor is maximized when the conductor is perpendicular to the magnetic field, and is zero when the conductor is parallel to the magnetic field. To find the direction of the force, we can use the right-hand slap rule that we introduced earlier in this video. The only difference this time is that the right thumb will point in the same direction as the conventional current. When this is done, along with pointing the four fingers in the direction of the external magnetic field, the direction away from the palm of the right hand will give the direction of the magnetic force on a current-carrying conductor. So in the example to the left here, we point our thumb upwards to match the current, and point our four fingers to the right to match the external magnetic field. And we see that the direction away from the palm of our right hand points into the screen, indicating the direction of the force on this conductor. We can now consider what happens when we have two current-carrying wires that are parallel to each other. These two wires have length L that are separated by a distance r, carrying currents I1 and I2 that are both directed into the screen. If we consider wire 1, it is carrying a current, so this must produce a circular magnetic field, and this will point downwards at the position of wire 2. Now notice how wire 2 is a current-carrying wire, and is at a right angle to the magnetic field produced by wire 1. So wire 2 must experience a magnetic force due to the magnetic field from wire 1. By pointing the right thumb into the screen and the four fingers downwards, we see that the force on wire 2 from the field of wire 1 acts to the left towards wire 1. The magnitude is given by the following expression, where B1 is the magnetic field strength of wire 1 at the position of wire 2, and I2 and L are the current and length of wire 2. If we now divide both sides by the length L, we can obtain an expression for the force per unit length on wire 2. This can be expanded even further to the following equation from the data booklet. This equation makes use of the fact that the magnetic field strength around a straight current carrying wire is proportional to the current in the wire and inversely proportional to the perpendicular distance from the wire. Similarly, wire 2 must also produce its own magnetic field, since it is a current carrying wire, and this field will point upwards at the position of wire 1. Therefore, wire 1 must also experience a magnetic force due to wire 2. From the right-hand slap rule, we see that the force on wire 1 acts to the right towards wire 2. Note that the magnitude of this force now has the magnetic field strength from wire 2 and the current and length of wire 1. But using similar analysis, the force per unit length on wire 1 is the same as wire 2. This shows that the forces on each wire are equal in magnitude but opposite in direction, even if both wires carry different currents. Moreover, when the currents are in the same direction, the forces are attractive and act toward each other. Now suppose that the current direction in wire 2 is reversed so that it points out of the screen, while everything else is kept the same. From the right-hand slap rule, we now find that the magnetic force on wire 2 points away from wire 1. If we now consider the magnetic field from wire 2, we also see that the magnetic force on wire 1 points away from wire 2. So the resulting forces act away from each other and push the wires apart when the currents are in opposite directions. Only the direction has changed, so the magnitude of each force and the force per unit length remain the same using the same analysis as before. We will now provide a final summary of the key understandings from this video. Magnetic fields are able to exert magnetic forces on moving charges, and on current-carrying conductors since current is a flow of electric charge. The magnitudes of these forces are given by the following two expressions, where both are dependent on the orientation of the magnetic field with the velocity of the charge and the direction of the current respectively. We use the right-hand slap rule to determine the direction of the magnetic force in both of these cases, where in particular we noted that the direction given by this rule is the direction of force on a positive charge. Moreover, we observed that a charge will move in uniform circular motion when its velocity is at right angles to a uniform magnetic field. Finally, we showed that parallel current-carrying conductors exert forces on one another that are equal in magnitude. The forces are directed toward each other when currents are in the same direction, and away from each other when currents are in opposite directions. This now concludes our video on magnetic forces. Thank you for watching.